Okay, so welcome back. And so now we're going to expand what we can do with logistic regression to allow for having more than one predictor of the outcome variable. So as in the case of linear regression, the strength of any modeling technique lies in its ability to be able to model many variables, and some of them could be on different measurement scales. So what we're going to assume is that we have a predetermined collection of variables that we are examining. And so this is a collection of p independent variables that are denoted by this vector x1, x2 up to x sub p. Okay, so I've got all these potential predictors. So the multiple logistic regression model states that the conditional probability, that is the probability that y is equal to 1 given all of these x's, is the probability that y equal 1 given the vector x, or the pi of x, where x is a vector, is given by pi of x is e to the beta naught plus beta 1 x1 plus beta 2 x2 all the way out to beta p xp divided by 1 plus e to the beta naught plus beta 1 x1 all the way out to beta p xp. Or we could write the logit as beta naught plus beta 1 x1 out to beta p xp. Well, we would simply be able to write this as e to the logit over 1 plus e to the logit. So that is our logistic regression probability. Now, if some of the independent variables are discrete nominal scaled variables like race or treatment group, then it would be inappropriate to include them in the model as if they were interval scaled. And so again, this is something that I think I alluded to previously, where if in fact your variable was coded 1, 2, 3, 4, but it's nominal scale, you would not want to put that variable coded 1, 2, 3, 4 in the model. You'd want to put them in as a set of dummy variables. Now in general, if a variable had k possible outcomes, there would be a need for k minus 1 dummy variables. And the notation that we're going to use is this. So let's say you were building a logit, and let's say that you have a variable, say x sub j, that has kj levels. So you would need kj minus 1 design variables to model the kj levels. And we're going to denote those with d's for the dummy variables. And so what we have is beta naught plus beta 1 x1, x1 might be age, plus beta 2 x2, x2 might be cholesterol. And then you finally get to the variable like perhaps race, and there you're going to have k minus 1 levels, or k minus 1 dummy variables that model the k levels of race. Okay, all of them get put into the model simultaneously. Okay, all of the dummy variables at once. Okay, so how do we fit the multiple logistic regression model? So let's assume then that we have n independent observations, call them xi, that's a vector xi and y, for I goes from 1 to n. Now as in the univariate case, we're looking for the maximum likelihood estimates of the parameters beta naught, beta 1, all the way out to beta p. So the likelihood function for the for the multiple logistic regression model is given by this. And again, this is the same as we had before. We have the product from I goes from 1 to n, and here is the probability that y is equal to 1 given x, the logistic probability, that's raised to the y-ith power. And then we have the probability that y is equal to 0 given x, or 1 minus pi of x, and that's raised to the 1 minus y-ith power. So clearly, you just tell me why. If the person does not have CHD, then we pick up this term. If the person does have CHD, we pick up this term. And so we have the product always picking up the right term depending on what the value of y is. Y is either present or absent. So in this case, there are going to be p plus 1 likelihood equations that are obtained by differentiating the log likelihood function with respect to the p plus 1 coefficients. So this then results in p plus 1 normal equations, which we would attempt to solve for beta naught, beta 1, all the way up to beta p. But that's not going to happen because the pi of x is this very complex expression, and so it's not going to be possible to come up with a closed form solution for the estimates of the coefficients. So instead, as with the univariable model, the solution of the likelihood equations requires special purpose software that can be found in many statistical packages. So let's let beta hat denote the solution to these equations. So the fitted values for the multiple logistic regression model are the estimated beta hats, estimated pi hats, where you basically take e to the logit over 1 plus e to the logit, computed using the estimated coefficients and the observed values of x. So it's easy to get this. Standard errors of the estimated coefficients are obtained along with the coefficients by any of the good computer packages, and these will be used for estimating the adjusted confidence intervals. So having said that, I want to take another example, and this example is called the low birth weight study. It's actually a very fascinating example, and I think before we get into it in any depth, this might be a good place for us to have a break. So let's have a break at this point, and then when we come back, we'll consider this example in detail.